Okay, so next video leads on from what we've been doing lately on finding stationary points, finding maximum and minimum points, x and y coordinates, and the strategy there has been to get the derivative and make it equal to 0. To find you the x coordinate, then put the x coordinate back into the original equation to find the y coordinate. And we've done that fairly well, with and without the calculator. So now we're going to apply it to more practical situations, okay, where we have to find a maximum or minimum value. This is a little bit of theory I've put. It's from the book, and it's just saying that if we've got a function called p, then we'll get a local minimum or local maximum. It may exist when the derivative equals 0. Okay, so just the same sort of thing as I've just said about that's been our method so far. Put may exist. Sometimes with these questions we limit our domain. Okay, so far we've been doing graphs that we haven't limited. But when you're talking about real life situations, you might be looking at the population of some animal between 0 and 48 months. Okay, so you look at the graph, you look at the function only between those two values. General strategy, find f-x, the gradient function. Solve for x, so make the derivative equal 0, and then solve for x to find the values of x where the maximum or minimum occurs. Sketch the graph if necessary. That really helps to see the pattern of things and where the maximum and minimum is. And remember to check endpoints. That is the domain limited? Then you can substitute those values of x into the original equation to obtain both coordinates of the maximum and minimum. So once you've found the x coordinate, it might be time, for example, you put the value for time back into the original equation to find the population. And finally, you need to show a point as a maximum or minimum by using a gradient table. Here's an example. The population of a colony of birds at any time, t months after observations began, can be modelled by the function p of t equals 400t e to the power of neg t on 5 plus 600, where p is the number of birds and t is in months. We have to find the initial population, when the largest numbers of birds is reached, so that's the value for t, and then the maximum number of birds, which will be a value for p. Okay, so B is very much involved with finding t, C is very much involved finding p. Alright, so the initial population. In any question involving populations and time, initial means t equals 0. So as soon as you see that word, there's a trigger moment, a light bulb moment, I've got to substitute t equals 0 to get the initial population or level of something. Okay? So that's what I've done here. I've taken the original equation and put t equals 0 into it. And any time you multiply three things with 0 in the middle, that there, with the purple box around it, will be 0 plus 600 equals 600 birds. Make sure, and I've underlined it there, you put in birds, not just 600. We're dealing with a certain quantity here, and it's the quantity or number of population of birds. So include the word birds, please. Alright, now we have to do the next bit, which is make the derivative. What we're doing next is finding the maximum number, when the maximum number of birds existed in this population. Okay, so to find maximum, we have to get p dash t equals 0. Now I could work this out on the calculator, but let's have a stab here at working out the derivative. We'll write the equation out again. So it's 400t e to the power of neg t on 5 plus 600. Let's have a stab at doing this without the calculator. Now, of course, the derivative of the 600 is going to be 0, so we don't have to worry about that. But here, you'll notice we've got a product. We've got 400t multiplied by e to the power of neg t on 5. So our strategy for using finding the derivative when we've got a product is the product rule. So we're going to use u equals 400t and v equals e to the power of neg t on 5. Okay, so there's our u and v values. Alright, so our du dt is going to be 400 okay, because the derivative of 400t is 400. dv dt, derivative comes out the front, the derivative comes out the front, so the derivative of neg t on 5 is neg 1 on 5, e to the power of e to the neg t on 5. Remember, the index doesn't change. Okay, so it's u times dv dt plus v times du dt. So our derivative, our p dash t, let's go back up here, it's going to equal, first of all, we've got to multiply 400t by that, let's go a bit bigger, that guy there. So 400t times negative a fifth, let's look at that, that's going to be negative 80t, so negative 80t e to the power of neg t on 5. Okay, so I've multiplied, if I just draw an arrow between these two here, I've multiplied those two together. Just pause the video here if you're unable to see how we get negative 80 t e to the neg t on 5. Let's see how you go with that. Alright, so moving on, then we're going to multiply the other two together. Okay, so across here, so that's plus 400 e to the neg t on 5. Now you notice here, I've got a common factor. So we can actually factorise this. E to the power of neg t on 5 is in both the left and right term there. But we can take more of that out because 80 actually goes into 400. We can actually take out a negative 80 e to the neg t on 5. If we take that out, we end up with t. Okay, so t is left there. If we take that out, and over here we've got negative 80 into 400 is negative 5. So we've got minus 5. Now we've got to make that equal to 0. So let's do that. So negative 80 e to the power of neg t on 5. T minus 5 equals 0. Now one of the obvious solutions to that is t equals 5 from the bracket there. Okay, so that's no problem. And what about outside the bracket? Well, we've got negative 80 e to the power of neg t on 5. Okay. Now, that, remember what we're doing here is we're making that equal 0, and that gives us t equals 5. We're also making the expression out the front equals 0. That has no real solutions. Okay. So we've only got one answer here, and I'll just make it a little bit neater than what I just did. Only got one solution here, and that's t equals 5. Alright, so our maximum value, that is our maximum population of birds, is 5 months, is when it occurs. Okay, and that answers question B. What we should probably do now is look at if that is a local maximum, and to do that we need to do a gradient table, and I've set one out here. I've put my 5 in the middle. Because there's only one maximum here, or one stationary point, we only need a table with 3 values because we're looking at what's happening the either side of that maximum value, the either side of 5. So to the left of the 5, I've used 0, and I've used 10 on the other side. Use the calculator here. What you find is if you put 0 into the derivative, okay, so p dash 0, we get a positive value. If I put 10 into the derivative, I get a negative value. Okay, so we get that pattern of plus 0, negative, which demonstrates that t equals 5 is a local maximum. The last question, question C, asks, well, okay, what is the maximum population of birds? We know it occurs at 5 months, so to find that out, we have to actually find p of 5 and put 5 into the original equation. So it's 400 times 5, e to the power of neg 5 on 5, plus 600. Now it would be very easy to dive to the calculator now to work this out. Okay, and you could do that. All right, no problem. But just want to give you a little hint here because it depends on how your mental arithmetic is a bit. But I would go a little bit further before I dive for the calculator. For example, I know that 400 times 5 is 2,000. I know neg 5 on 5 is neg 1 plus 600. Then put that into the calculator. In fact, you could even make that 2,000 over E if you wanted to. It doesn't matter. Okay, and then if you do that, you can find the answer to the population, and it equals 1,335.8. Now, the maximum number of birds, you don't round off in this situation because you haven't actually reached the 1,336th bird yet. Okay, the number of full birds you've got, and that sounds weird, the number of full birds you've got is 1,335. Okay, so 1,335 birds would be the answer. Let's move on now to a second example. I want to do this question as an example of one that can be done without a calculator. I don't want us to get the impression that all maximum and minimum problems will be in the calculator section. A lot of them are likely to be, or it's more likely to be, but they are fair game for the non-calculator as well. So that's why I thought I'd include this example. I'm going to do it totally without a calculator, unlike the first one where we used it a little bit. Alright, so we've got the displacement of a particle. For those who do physical science, it's probably most of you, you know about displacement and velocity, etc. Displacement of a particle moving in a straight line from the origin at any given time t is given by x of t equals a third t cubed minus 4t squared plus 12t plus 1, where t is between 0 and 7. So I talked earlier in this video about domain restrictions, and there's an example there of a domain that's been restricted. Find the maximum and minimum displacement. Alright, so maximum, minimum, as soon as we see that, biggest, smallest, largest, we get derivative and make it equal to 0. So let's find x dash t, so x dash t, derivative of our function. 3 times a third is 1, reduce the index by 1 is t squared, minus 8t plus 12. Okay, pause the video here if you want to have a closer look at how to get that derivative, but they're straightforward ones that we would have done earlier in our unit on getting derivatives, and also you would have done last year. So there's that one. Now we make it equal to 0, so x dash t equals 0, so t squared minus 8t plus 12 equals 0, t minus 6, t minus 2 equals 0, so t equals 6 or 2. Check at this stage whether both those answers are in the domain. Of course they are, because the domain is t is between 0 and 7 included. Alright, so now we have to look at doing our gradient table. Right, so I've set up the gradient table here of 2 and 6, and we're going to surround these numbers with numbers either side of 2 and 6. So we've got 0 is a good choice here. We can put 4 there and 8 there. It doesn't really matter as long as those numbers fall in order. We know that if we put 2 into the derivative, we get 0 because it's a maximum or a minimum, same with 6. Alright, so what we do now is we put those values 0, 4 and 8 into the derivative. So x dash 0 is going to equal 0 squared minus 8 times 0 plus 12. So we're going to get a positive value there. X dash 4 is 4 squared minus 8 times 4 plus 12. That's 16 minus 32 plus 12. That's going to be negative 4. Negative value. X dash 8 equals 8 squared minus 8 times 8, so that's 64 minus 64 already, plus 12 equals 12, positive value. So our slopes are, we've got positive, 0, negative, 0, positive. So that tells us a little bit about our stationary points that occur at 2 and 6. What we'll do now is we'll put 2 and 6 back into the original to find the y coordinates of those turning points. Okay, so just a moment. So now we know that the turning points are at x equals 2, x equals 6. We also know that 2 is going to be a maximum and 6 is going to be a minimum. How do we know that? We know that from our patterns here, okay, of our gradients. So let's put 2 back into the original. We get x of 2 equals a third times 2 cubed minus 4 times 2 squared plus 12 times 2 plus 1. It's going to be 8 on 3 minus 16 plus 24 plus 1. Okay, and that's going to be, let me see, 25 minus 16 is 9. I think that's going to be 11 and 2/3. So 2 comma 11 and 2/3. That's a maximum. Gradients are, if we look back here, positive 0 negative, positive 0 negative. Okay, now we need to put 6 back into the original. So put 6 back into the original, so it's a third times 6 cubed minus 4 times 6 squared plus 12 times 6 plus 1. Okay, so that equals 72 minus 144 plus 72 plus 1. You might think, oh, there's no way I could do that without a calculator. Okay, but you may need to in the exam. Okay, those sorts of calculations, are fair game. So that's going to be 1. So we've got 6 and 1 is our other point. Is a local minimum. I don't think I used the word minimum before. Sorry about that. The word local before in the last one. Did I? Let's just let me have a look. No, I didn't. So it's local maximum. Sorry about that. Yeah, as local minimum, as gradients are. Go back to our table. Our gradients were negative, 0, positive. 0, positive. Alright, let's wrap up then. We've got these 2 points. We've got 2 comma 11 2/3, and we've got 6 comma 1. I want to link now back to the original question, which said find the maximum minimum displacement. Okay, it mentions, doesn't mention the time, just the displacement. So we know that our maximum displacement, and we must write this at the end of the question, maximum displacement is 11 and 2/3. Now, there are no units mentioned as far as metres or centimetres. So, in that case, what we usually do is just put units. Okay, so 11 and 2/3 units, and the minimum displacement is 1 unit. So there we go. That's an example of a question which doesn't involve graphing, and it doesn't involve using the calculator necessarily. Okay, so all the mathematical skills there would be fair game in the non-calculator section. That's why I thought it was important to do that. Alright, so you can have a go now. The same sort of procedure occurs with finding maximum, minimum. Find the derivative, make it equal to 0, show whether it's a maximum, show whether it's a minimum, and you can substitute the x value into the original to find the other coordinate. All those sort of things apply. So you now have a go at exercise 8C, which we're going to work on Tuesday.